Hello, in addition to my last video, which was on the subject of dynamical systems, we solved a system for a linear oscillator. Now, I want to go a bit further by doing a similar example, the one that you see here on the whiteboard, where we have x dot equals x minus 2y and y dot equals minus 3x plus 2y. We're going to do exactly the same sort of thing with this in order to solve it and find two general solutions, one for x in terms of time t and one for y in terms of time t. So, excuse me. As I said, we're not going to do the usual thing by dividing y dot by x dot, because that would just give us two solutions, one in both in terms of x and y. For example, if we divided y dot by x dot, we either get a solution for y in terms of x, or the other way around. I think you would just get x in terms of y, or something like that. So this time we want two solutions that give x and y in terms of time t. So we're going to make a start solving this system. So I'm going to call this x dot. So that's your vector. X dot is equal to little x dot and y dot. So that's the vector, and that's equal to the matrices. Well, this is x minus 2y. You could start off by writing x minus 2y like that, but we don't want to have the x's in the matrix. We want 1 and minus 2, and multiply the vector xy on the right hand side. So you multiply that matrix by the vector with x and y contained within it on the right hand side. This equation, y dot is equal to minus 3, and that's 2. So you can see, if you re-multiply this out, 1 times x gives you x, minus 2 times y gives you minus 2y, and minus 3 times x is minus 3x, and 2 times y is plus 2y there. Now, as before, what we do is we write down the matrix A, and we know what that is because we've got it here. So I'll just delete that line for a moment, and we'll write down 1, minus 2, minus 3, and 2. Okay? So that is the matrix A. Now, from that matrix, we can see that these entries, the top row of entries and the bottom row of entries, are not multiples of each other, which implies that in that case the determinant of A is not equal to 0. And of course we can prove that because the determinant will be 1 times 2 minus 2 times minus 3, which is equal to 2 minus 6, which is equal to minus 4. Now that tells us, because the determinant of A is not equal to 0, that tells us that we can form a characteristic equation a characteristic equation by finding, by finding the determinant of I'm going to call it lambda I minus A, or we've put the modular signs in, lambda I minus A. Okay? Right, so if you remember back to the last video, I explained why I take this to be lambda I minus A. In the book from which this example comes by D.W. Jordan and P. Smith, the title of the book is Non-Linear Ordinary Differential Equations, An Introduction to Dynamical Systems. I'm quoting from the third edition, which I think was printed getting on for 20 years ago. This example is example 2.6 in the book, which occurs on, I think, page 60. So page 60 of that book. Oh, this is example 2.6. So I should have stated that at the beginning, but never mind. I choose to find the determinant writing it down this way rather than the book's way, which is to find A minus lambda I. And that's because I don't want rather irritating minus signs that might lead me to the wrong answer, because I make mistakes with minus signs. So that's why I am sticking with this method of finding the determinant. So we've got lambda I minus A, and I'm going to change pens because I think that one's starting to get a bit weak and running out. So we've got lambda I minus A, and that's equal to I'll write it down this way. Lambda times the identity matrix 1 0 0 1 minus 1 minus 2 minus 3 2. Okay, now like I explained in the last video, that simply becomes lambda 0 0 lambda minus, in bracket, in the matrix again, 1 minus 2 minus 3 2. So we can rewrite that as lambda minus 1, and of course it should really go in these kind of modulus signs. So it's lambda minus 1, a minus 0 or 0 minus a minus 2 is just plus 2. Then we've got 0 minus minus 3, which is just plus 3. And then we've got lambda minus 2. Lambda minus 2. Okay? So the characteristic equation is now found by multiplying lambda minus 1 by lambda minus 2 minus 3 times 2. So let's write that down. Lambda I minus A is equal to lambda minus 1 times lambda minus 2 minus 2 times 3. Okay, so we have that, and this comes out to be lambda squared minus 2 lambda minus lambda plus 2 minus 6. And that simplifies to give lambda squared minus 3 lambda minus 4. And that has got to be equal to 0, as it should have been down here. Right? So we should be able to factorise this in this case, and that factorises to give lambda and lambda there in the brackets, minus, and we've got to have a plus somewhere as well, because when we multiply whatever the minus number is by the positive number, it has to equal 4. So let's think about that for a moment. We know that 1 and 3 gives 4, so minus 1 times plus 3 is minus 4. But what is minus 1 plus 3? Because we need the sum of those two numbers to equal minus 3. Well, it can't be minus 1 and plus 3, because if you, or minus 1 and plus 4, because when you subtract 1 from 4, it gives plus 3. So we must have plus 1 and minus 3. Sorry, minus 4. I seem to have 3 on the brain. We'll just check that that works. So if we multiply this out again, we get lambda squared minus 4 lambda plus 1 lambda minus 4. So that's lambda squared minus 3 lambda, because minus 4 lambda plus lambda is minus 3 lambda minus 4. So we know that we've got the right factorised form of the characteristic equation. So we'll just rub that out in red, rub the red part out, and this tells us that therefore the eigenvalues are lambda equals, well, first of all we've got, let me just rub that little bit out. So we'll go through this step by step. So therefore lambda plus 1 equals 0, or lambda minus 4 equals 0. This implies that lambda equals minus 1 and lambda equals 4. Now the book does it. The book takes this value first to work out the next, or the first eigenvector. But I took lambda equals minus 1 to be the first eigenvalue to lead to the first eigenvector. All that it does is that your constants get switched around in the final answer, and but that doesn't really matter, because your constants will come out to whatever they are when you put in the initial conditions. But I'm going to do it my way, starting with lambda equals minus 1. So we know that the det lambda I minus A is equal to, in fact I'm actually going to call this matrix B. So matrix B is equal to this matrix here, lambda minus 1, 2, 3 and lambda minus 2. Okay, now we have an x and a y term there in that vector. So when lambda is equal to minus 1, that is one of our eigenvalues. So I'll just write that down. Lambda equals minus 1 is our first eigenvalue, in case I didn't mention it before. So that's our first eigenvalue. So when lambda is equal to minus 1, we substitute it back into here, and we get B equals minus 1 minus 1. That stays as 2, that stays as 3, and we've got minus 1, minus 2 there. And don't forget to put in your x and y vector. Right, so B becomes, in fact, I'm going to call this B, that's B, so this is B1, B1, because it's different depending on which eigenvalue you resubstitute. And I probably didn't do this in the last video, but hopefully you got the gist of it there anyway. So this becomes minus 2, 2, 3, and minus 3. And for this to work, B has to be equal to 0. So this means if you cancel the top line by 2 and the bottom line by 3, or rather if you cancel the top line by minus 2 and the bottom line by 3, we just get a single equation because each of these is a multiple of that single equation. This is a multiple of 2. This is 2 times that equation, which is x minus y equals 0. So that is minus 2 times that equation. That is 3 times that equation. And of course, if x, and we could use any values for x and y that make that equal to 0. We can't work x and y out. All we can say is that x and y have infinitely many values that make that equation equal to 0. You could probably choose 1,330,000 there and 1,000,000 and what was it I said, 33,000 there, and that would make the equation equal to 0. So that would be one eigenvector. So, but we choose simple values. So I'm choosing x to be equal to 1 and y to be equal to 1, because as you can see, when you substitute 1 in for x and 1 in for y, you get 1 minus 1, which is 0. Right? So we'll just rub that out, because we found now an eigenvector which we'll call V1. So therefore V1 is equal to some constant A times 1 and 1 in the vector. So that is one of our eigenvectors. Now, what about the other eigenvector? Well, let's just rub that out and make sure we have a dividing line so that we're not drawing over things, writing over things. So when lambda is equal to 4, this is second eigenvalue. Second eigenvalue. Then B is equal to, well, we've already stated it up there, B. So we'll call this B2. So when lambda is equal to plus 4, we've got 4 minus 1. That's why I'm calling this B2. So 4 minus 1. That 2 stays exactly the same. And the 3 down here stays exactly the same. And then we have 4 minus 2 here. And in actual fact, we want to make that into a matrix with the xy vector there. And that has to be equal to 0. So B2 is equal to 3, 2, 3, 2. As you can see directly from that. X, Y equals 0. Right, okay, 4 minus 1 is 3, the 2 stays the same, the 3 stays the same there, and 4 minus 2 is 2. Therefore, we have identical equations, 2 identical equations, which are 3x plus 2y equal to 0. Okay, so I'm going to try and stick with what I did in my notes because yeah, okay. So we want a value for x, which when multiplied by 3 cancels with a value for y multiplied by 2. Well, if you choose x equals minus 2 and y equals 3, then we can test those two values. You could have chosen x equals plus 2 and y equals minus 3. That would have been admissible. But the thing is, when you work the constants out in the end, they're going to define the particular solutions anyway, which will either allow minus signs and plus signs to remain, or it will get rid of them, regardless of where they are in the working at this point. So that's why it doesn't really matter what your values are and what their signs are, so long as they equate each of these kinds of equations to 0. So we've got 3 times minus 2 plus 2 times 3, and that's equal to minus 6 plus 6, which is 0. So we've got the components of our eigenvector v2. So v2 equals some constant. In fact, there I called that A, and that might get mistaken for this matrix here. So I'm just going to call that C1, and we'll call this C2 times minus 2 and 3. So all I've done is change the constants because I didn't want to confuse them with notation like this A and this B that I've used before for other things. So many apologies for that. I hope you understand why I've suddenly changed that from an A to a C1. It's just to be consistent and particularly not to be inconsistent. So we can now write down our general solutions. So the general solution is, well, this time it's going to be our vector x, and that's going to be equal to x and y, not x dot and not y dot. X equals our vector xy, which is equal to, right, well, in the first case we've got an eigenvalue of minus 1 associated with this eigenvector down here. So that's going to be C1 times 1, 1 as the eigenvector. I'm trying to make these ones look a little bit more convincing so that you can see what I'm writing. Times an exponential, well, it's minus 1, so we're going to have a minus 1t here, or just e to the minus t, plus c2 times minus 2, 3 times e to the power, well, we've got an eigenvalue of 4, so it's going to be plus 4t. And that basically is your answer. Now, I'm just going to break this up and write it down as 2 separate equations, not in matrix form. Okay, so we've got x of t equals, well, we've got c1 times 1 e to the minus t, c1 e to the minus t, plus, Well, actually, it's going to be a minus 2c2 e to the 40. Minus 2c2 e to the 40. Okay? And for the y equation, or the y solution, we've got, again, we've got c1 e to the minus t. And we're going to have plus 3 times c2 e to the 4t. And that is the answer. Now, I'll just say one last thing, that in Jordan and Smith, they have the equations this way round. So x of t is equal to, let me see what they've got. If I can quickly flip to it. Right, yeah, so they've got minus 2c1 e to the 4t plus c2 e to the minus t. And y of t equals 3c1 e to the 4t plus c2 e to the minus t. And I'll just double check that, and I'll explain why they've got that. Perfectly admissible again. Yes, minus 2c1 e to the 4t plus c2 e to the minus t. And for y, we've got 3c1 e to the 4t plus c2 e to the minus t. And the reason why they have got the solutions in that form with the c1 and the c2 interchanged is simply because I took the eigenvalues in reverse order to them. They took the first eigenvalue to be plus 4, and they took their second eigenvalue to be lambda equal to minus 1. I chose lambda equals to be equal to minus 1 first, and then lambda equals 4 second. That's why there's a slight change in the constants, but it's perfectly admissible and perfectly okay. And of course, you can plot these on a phase plot or a graph. I'm not going to do that at this stage because there isn't really enough time. But so long as you can get to these solutions, and maybe at some future date, we will look at how to plot these solutions. And sometimes you use different analytic methods to do that. So I hope that has been okay for you, and again that it has helped you in your quest to understand this sort of non-linear dynamic systems material. And I am going to be putting up another video in a short while which continues with this, but using complex numbers. So that's going to be my next video, so I hope you tune in to watch that, and also that you will tune in and watch any previous videos of mine. Again, apologies if I make mistakes. I make mistake after mistake and forget things. So my videos are not perfect, but hopefully you will be able to work round those errors that I make and still get something out of the videos and learn appropriately even so. So I'll bid you farewell for now. Take care, and I'll see you in the next video. Okay, cheerio then, bye.